Hi everyone, my name is Claire Tomlin and I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 18th module in a series that we're recording to support the course Linear System Theory EE221A at Berkeley. In this module, we're going to introduce what is called the state transition matrix. We're going to use that to define or construct and then show what the solution to a linear time varying system in terms of a vector differential equation that we discussed in the last module is. And so we recall from our last module that we introduced module 17, that we introduced the concept of a differential equation, x dot is equal to a of t x of t plus b of t u at t, with some initial condition x of t0 is equal to x0. Okay, so that's what we called, or will call now, our vector differential equation. And we discussed in our last module this as a differential equation which describes a linear time varying system. In order to actually show that it's linear, we have to construct the response function of this dynamical system. But in order to do that, we have to construct the state transition function. So we have to understand how the state transitions from one value at time t0 to a value x of t at time t. And in order to do that, we need to solve that differential equation. Okay, so we showed that that differential equation is Lipschitz continuous in x, so there exists a unique solution to that differential equation for that initial condition. And so we're going to now construct the solution in the next two modules, this one and the next one. We'll construct the solution to that vector differential equation by defining a solution to a corresponding matrix differential equation in the following way. So we're going to step back from that vector differential equation and think about the following matrix differential equation. So we'll call that MDE for matrix differential equation. And instead of x being a vector in Rn, I'm going to use the notation capital X, x of t, and I'm going to construct the following differential equation for a given initial condition. X at t0 is equal to matrix x0. Okay, so here, A of t, it's the same A of t matrix that we had in the vector differential equation. It's an n by n dimensional matrix. What's changed, apart from we also don't have a b and a u here, is that X is a matrix. It's an n by n dimensional matrix. And this is called the corresponding matrix differential equation. So these are all n by n dimensional matrices. Okay, so we're going to consider that matrix differential equation, and we will consider the solution to that matrix differential equation starting at a particular initial condition, which is the identity matrix. So first of all, we just note that this differential equation is piecewise continuous in time, and it's Lipschitz continuous in the matrix X. Again, the Lipschitz function that we use to show Lipschitz continuity is the induced norm on the matrix A. Okay, so from our previous work, we can easily show that that matrix differential equation satisfies the conditions of the existence and uniqueness theorem. Okay, so our next step, we're going to define a matrix, and I'm going to call it phi of t, t0. That is defined to be the solution to the matrix differential equation above with the initial condition phi at t0, comma t0 to be the identity matrix. Okay, so phi is an n by n matrix, and it's written explicitly in terms of the current time and the initial time, but it's the solution to that differential equation starting at an initial condition, which is the identity matrix. Given that definition of phi, which has a very special name, it's called the state transition matrix, for reasons that we'll see. We can define solutions to the corresponding vector differential equation. Okay, so the first thing we're going to do is just look at a couple of properties of phi. The first property is that if you look at the vector differential equation with the input zeroed out, so just look at this part of the vector differential equation. The first property is that the solution to the vector differential equation, x dot is equal to a of tx. Here, x of t is a vector in Rn, so we're back to our vector differential equation, is given by x of t is equal to phi of t, t0, the state transition matrix, times the initial condition for the vector differential equation. So that's given here. Okay, so we've defined, this requires proof, but we've stated that the solution to the vector differential equation is a function of the solution of this matrix differential equation, multiplied by the initial state for the vector differential equation. The second property is a property of the state, a property which is intrinsic to this state transition matrix. Phi of t comma t0 is equal to phi of t comma t1 times phi of t1 comma t0. This is called the semigroup property. We recall the statement of the semigroup axiom from our definition of dynamical systems, and this is strongly related to that, as we'll see. But again, this requires proof. We have to show that this matrix product is equal to the corresponding state transition matrix on the left-hand side. The third property is that the inverse of the state transition matrix, phi inverse of t0, exists, and it's given by phi of t0 comma t, which is somewhat surprising. So all three of these require proof. We will prove the first two, and we can prove them just by showing that these functions of time satisfy the same initial condition and they satisfy the same differential equation as long as that differential equation has a unique solution. And by that, if you show two functions of time satisfy the same initial condition and the same differential equation, then you've shown that those functions of time are equal to each other by the existence and uniqueness theorem. So we'll show the first two properties, and the third property you can show yourself. Okay, so the proof of one is as follows. So x of t solves that differential equation. So if you want to show, let's call this the left-hand side and this the right-hand side. So let's show that the left-hand side as a function of t satisfies the same initial condition and the same differential equation as the right-hand side. So x of t0, so left-hand side at time t0 is just x at time t0, which is x0. The right-hand side at time t0 is equal to phi at time t0 comma t0 times x0. This is the identity matrix as defined, so that's just equal to x0. Okay, so they both satisfy the same initial condition, and indeed they both satisfy the same differential equation. By definition, x dot is equal to ax, so the left-hand side differential equation is just given by definition because x of t is defined to be the solution to that differential equation. And then on the right-hand side, we just have to take the derivative of that function of time. So here it depends on time. So the right-hand side, phi dot of t, t0, x0 is equal to, by definition, a of t, phi of t, t0, and then we multiply that by x0. Okay, so that's the differential equation. We have that function, the derivative of that function is a of t times that function. So it satisfies the same differential equation. So since both functions satisfy the same initial condition and they satisfy the same differential equation, and that differential equation satisfies the existence and uniqueness theorem properties, that tells us that the two functions of time are equal to each other. So right-hand side is equal to left-hand side. And we can follow the same strategy for the second property. Okay, so let's prove 2. Show that they satisfy the same initial condition and the same differential equation. Here I'm going to generally define my initial point in time to be t1 because it's easier to show here. It doesn't really matter at what point in time you show that those functions are equal to each other. As long as they're equal to each other at one point in time and they satisfy the same differential equation, then that's enough to show that the functions of time are equal to each other. So I'm going to show that they're equal to each other at time t1 is equal to phi of t1 comma t0. And the right-hand side at time t1 is equal to phi of t1 comma t1 times phi of t1 comma t0. And this is equal to the identity by definition. It's not t0 comma t0, but in fact, this, as we said, the initial condition could be any given time. And so just as long as these two time points match, then that matrix is equal to the identity. Okay, so that's just phi of t1 comma t0. So the functions are equal to each other at time t1, so there exists a point in time at which the functions are equal to each other. And now let's show that they satisfy the same differential equation. Excuse me. Okay, so we'll do that down here. Let's keep this on the board. So in the left-hand side, the differential equation is just phi dot. And so we know by definition that phi dot of t comma t0 is equal to a of t phi of t comma t0. Okay, so that's the differential equation that the left-hand side satisfies. Let's look at the right-hand side here. So in terms of the right-hand side, the only term that depends on time in this product is the first one. The rest depend on t1, t0, which are fixed. So again, the derivative of that is just going to be a of t phi of t comma t1 times phi of t1 comma t0. Okay, so again, the differential equation, when we take the derivative of that right-hand side, it satisfies a differential equation which is derivative is equal to a of t times the function itself. So the derivative of the right-hand side is a of t times the right-hand side. Again, the left-hand side, the derivative of the left-hand side is a of t times the left-hand side. So they satisfy the same differential equation. So they satisfy the same initial condition. They satisfy, where did we do that? They satisfy the same initial condition. They satisfy the same differential equation. So these two functions of time are equal to each other. Okay, so we've got these two pieces. Okay, so what have we done here? We've constructed something that's going to be useful in the construction of the vector differential equation. We could see that from that first property that we proved, that when we remove the input, the solution to that vector differential equation depended on this matrix, which we've defined to be the state transition matrix, which we've called the state transition matrix. We've defined it in terms of the solution of the corresponding matrix differential equation. So we constructed a matrix phi, which by definition solves a matrix differential equation with initial condition being the identity. And then we use that matrix phi to define the solution, or to construct the solution to the vector differential equation when the input is zeroed out. And we talked about properties of that matrix phi. In the next module, we will derive the solution to the full vector differential equation, the one where we have the b of t, u of t term in there, in terms of this state transition matrix phi, and we'll discuss its properties. Thank you.